Okay guys, so section 18.3 is about how to do all the math for what we've already talked about. So it starts you off explaining we already solved for KEQ using known concentration values, but every once in a while it'll want you to solve for one of the variables after you already know the KEQ. So on page 576, number 16 in your book, okay, we're going to do that problem together. We're just going to do A and B so I can walk you guys through how to do those problems, and then that way you should be able to practice them on your own and get really good at them. So what it wants us to do is on part A, it tells us that the KEQ for this reaction is 10.5. So instead of having to calculate it, we're going to use that number to figure out the other numbers. So at that point in time, it says that hydrogen has that concentration and the methanol has this concentration. So again, the first thing you got to do is build your equation based off the chemical equation. So we're going to have a KEQ that's the product divided by the reactants raised to their coefficients. Okay. Once you get to there, you substitute these two numbers as well as the KEQ in for the variables, and we solve for the one we don't know. So for this one, we don't know CO. So what I'm going to do is I'm going to bring the CO over here so I can isolate it and get it out of the denominator, which means I would eventually have to divide by the KEQ, which means that I can say the concentration of CO has to equal the CH3OH, which is 1.32, divided by the KEQ, which is 10.5, times the hydrogen squared, which is 0.933 squared. And remember, on your calculators, it's really important that you push the divide sign both for the 10.5 and the 0.933 squares. And so I'm going to do that real quick for you. So if you type 1.32 divide 0.5 divide 0.933 and you push the x squared button on your calculator, you will get 0.144, and this is a concentration, so it is in molarity. Okay. So the trick is on this one, you just got to be able to move whichever variable you're trying to solve for to one side all by itself, plug in the numbers, and then go. Okay. Part B is a little trickier because now we're solving for something that has a 2 in front of it. Okay. And so we're going to have to do the square root on this one, but it's solved the same way. So we're going to do KEQ equals the CH3OH divided by the CO times the H2 squared. Making sure we got that down. Again, it's always products divided by reactants. But now we're solving for H2. So just like up here where we had to swap the KEQ and the CO, we're going to do the same thing, but then we need to get that squared out of there. And so what we're going to end up doing is the concentration of H2 is going to be the square root of the CH3OH, which in this case is 0.325, divided by the concentration of CO, which is 1.09, and the KEQ, which is 10.5. And again, we're going to grab our calculator. And you got to do what's inside the square root first, or if you want to use a bunch of parentheses, you're more than welcome to do that. But to me, it's easier to just do 0.325, divide by 1.09, divide by 10.5, and push enter. And then you can do the square root of that answer. And we get 0.169. And again, it's a concentration, so it's got to be molarity for our concentration. Okay? So that is how you do any of these problems where you know your KEQ value, but you don't know one of the reactants or the products. Okay? Then the next section shows you how it ties into solubility. So what we've got here is just a simple, we're going to take calcium fluoride salt, which is a solid, and we're going to make it aqueous. We're going to dissolve it in water. Okay, so we're going to figure out the solubility of this. Now, this is a heterogeneous equilibrium. And so like we talked about in the first video for this chapter, you don't have to keep track of S's whenever you're doing constants. And so this just becomes the concentration of calcium cations times the concentration of fluorides squared. So it's the same K value that you would do for any other equation. We just call it SP instead of EQ because this is a solubility product. So we're multiplying the ions that are in solution. Okay? So once you get this formula set up, you can figure out from this point, no matter how much calcium fluoride you add, okay, you're going to end up getting 2.06 times 10 to the minus 4 calcium in the water, and you will always end up getting 4.12 times 10 to the minus 4 fluoride. And if we do this, you should get 2.06 times 10 to the minus 4 times 4.12 times 10 to the minus 4 squared. Your calculator should spit out 3.5 times 10 to the minus 11. And again, that is a K. I don't need you to know the units, just that is the number that it is. Okay? Which means calcium fluoride does not want to dissolve in water very much. So this is one that we said would be soluble back when we first learned solubility rules, but this is the actual amount of ions that water can hold for this substance. And so where that's important is up until now we've only been saying this chemical is soluble or this chemical is usually insoluble. The problem is every substance is always soluble up to a certain number. And so I'm going to show you how if you know this, you can calculate these two numbers by yourself. So that's the next part is, can you solve for KSPs if you're given this? And the part right after that is, can you determine the solubility if you already know the KSP? So in order to do that, I'm going to erase this. Okay? And then we've got to go back all the way back to moles and understand that no matter what, for every one of these that we put in the water, we always get 1 calcium and twice as many fluorides. So if we're ever asked for these things that we don't know, we have to call this one X, and we have to call this one 2X. this number must be twice as many ions as this number. And so now, we still have our same equation, which is going to be the concentration of calcium times the concentration of fluoride squared. But now we're saying that we already know the 3.5 times 10 to the minus 11. We don't know how much calcium there is, and we don't know how much fluoride there is, but we know that must be true. And so following our order of operations from math class, we get 3.5 times 10 to the minus 11 equals 4x cubed. So remember, you got to do 2x times 2x first, which gives us 4x squared, and then another x makes it a cube. So to solve for this, we divide both sides by 4, and then we do the cubed root. So x equals the cubed root of 3.5 times 10 to the minus 11 over 4. And when you do that on your calculator, okay, you should get x equals 2.06 times 10 to the negative 4th, which I know is not correct sig fig wise, but I want you to make sure that your calculator gives you that number. And because this was only two sig figs, we would round this to 2.1 times 10 to the minus 4. And because it's x, that tells us that we have that much calcium, and we should have twice as much fluoride, which if you times this by 2, you get 4.2, which on the previous problem is the two numbers I gave you, okay, because I cheated and I wrote the numbers down up there so that I didn't have to look them up while I was doing the video. But this is how much calcium is in the water, and 4.2 times 10 to the minus 4 is how much fluoride is in the water. And as long as you understand that for every one of those, you get one of those, you can now say the solubility of calcium fluoride at this temperature is equal to 2.1 times 10 to the minus 4. Okay? So it's the ability to work forward through the math to get your K, or if you have your K and you don't know what's in the water, it's being able to work your way backwards to figure out how much stuff is in the water. So that gets us through the first half, and in just a second I'm going to go through the second half. Now that we know how to calculate KSP, we are now going to start using math to predict precipitates instead of just the generic, yes, this is soluble, no, it's not soluble. Because even substances that we say are not soluble will dissolve up to a certain number. And so what we have is our KSP, which is the solubility product telling us that this many ions can dissolve. So if we're using water, the water can dissolve up to the KSP number, and then anything above the KSP number cannot go into water. And so we don't get confused with two different Ks. We use the letter Q to represent the trial that we have. So if we are trying to dissolve lead chloride in water, we're going to create a concentration of that, which would be our Q, and we're going to compare that to our K and see if it will or will not dissolve. And so that brings us back to some older vocabulary words. So what we always do is we take what we've got and we compare it to the solubility product. If we have less than what the water can hold, then this solution is unsaturated. which means you will see no precipitate and it will fully dissolve. And you could even add a little bit more, okay? If you somehow get your Q to be equal to the KSP, then you are at the maximum that the water can hold, which is our word saturated, which means that it will dissolve, but if you put one more little drop of what we're trying to put in there, it will no longer dissolve. And if your Q is greater than what the water can hold, then you will see a precipitate. Okay? So knowing the general solubility rules is useful. So knowing that ammonium nitrate will dissolve in water really, really well, that just tells you that it has a very, very large KSP. There is a point at which even ammonium chloride cannot dissolve in water anymore. It's just a lot. Okay? But for some of the other salts that we have said all year long are not soluble, not soluble, not soluble, technically they are soluble up to a very, very small number. So we are trying to determine if we have reached that number or not. So next we're going to do a couple of problems with this. Okay, so now we're going to try to prove whether a precipitate or not, or will form or not. So if you in your books on page 583, number 19, it tells us that we're going to mix equal volumes of 0.10 molarity lead nitrate and 0.030 molarity sodium fluoride, and it wants us to predict whether a precipitate will form or not. Using our rules from earlier in the year, we would assume that the lead fluoride is the one that is the precipitate, because this one is always aqueous with an alkali metal and a nitrate. But we need to actually prove whether a precipitate would form or not. And so this problem requires you to do a couple of things from earlier in the year. I looked up in the table, which the book says use this number from the table to produce a precipitate or not. So we wrote down the KSP for lead fluoride is 3.3 times 10 to the minus 8. So the most important part here is to understand if you're mixing equal volumes of this, then when you mix them together, this concentration is going to be cut in half, and this concentration will also be cut in half. So what we really have is 0.050 concentration of this and 0.015 concentration of that. Because if they were that strength before we mixed them, once we mix equal volumes, it doubles the volume, but it changes the moles, so we have to cut the molarities in half. Now, why that's important is because for every one of these molarities, we get exactly one lead, and for every one of these, we get exactly one fluoride. And so if we're looking at this substance right here, PbF2, we need to know if it becomes aqueous, what is our equilibrium equation? So just like we did before, it's going to be lead times fluoride squared, but we need to make sure that we call this a QSP because this is using our actual chemicals that we're mixing together. And so we know the QSP must be the Pb plus 2 times the F minus squared, which means that we have 0.05 times 0.015 squared. So if you grab your calculator, you do 0.015 squared and then you multiply it by 0.05. And we get 1.1 times 10 to the minus 5. And now this is important because now we're going to bring this number up here. Okay. Our QSP is 1.1 times 10 to the minus 5, and our KSP from the chart was 3.3 times 10 to the negative 8. So we're going to compare these two numbers, and this one has a negative 5 exponent, that one has a negative 8, so we have way more in our equation than what the water can hold. And so we would say, yes, a precipitate will form. Okay. In a more advanced class, it might ask you to calculate how much precipitate would form, and that wouldn't be too bad because then you would just have to do some math with this number and that number, but we don't have to do that for our class. And so this is how to use your solubility product to prove whether a precipitate will form or not. If your QSP was a smaller number than that, then you would say no, a precipitate will not form because the solution is unsaturated. Alright, the last thing in chapter 18 that I need to cover is the common ion effect. Okay, so up until this point in the year, we've just been worrying about one chemical in solution, never two at a time, but this is where we're going to start asking what will happen if we mix chemical 1 and chemical 2 together. And so what we get is the common ion effect, which basically says that if you add another substance with a common ion, it will affect the solubility product of the original solution, because the water can only hold this KSP. So if you increase or decrease one of the pieces, it will force the other one to go up or down as a result. So we're going to do the same one the book did with you together, which is lead 2 chromate. Putting it in water will create lead ions and chromate ions. And we know that the KSP for this is already 2.3 times 10 to the minus 13. So again, we need to put together our KSP equation, which is just the lead times the chromate. And we know that this is X and this is X. No coefficients or anything like that to make it nice and easy, which means that the concentration of lead is going to be the square root of our KSP. So if we just plug everybody in, that equals X squared. So if you do the square root of that, we get 4.8 times 10 to the minus 7. So the lead and the chromate, because they're both X, will be that number. Okay? That's from the last lecture, but now we're going to ask ourselves, once we already know that fact, what would happen if we were to just add potassium chromate to this solution? And so what we're going to do is we're going to add enough potassium chromate to make the concentration of it 0.1. So the first thing you need to look at is look at this number compared to that number. Because currently the lead and the chromate are both equal to that number. Okay? This number is really, really big compared to that number. So even if we wanted to subtract them, that number does not ever affect this number where our significant figures are. So what we can do is we now pretend that the concentration of the CrO4 in the solution is just this 0.1 molarity that we added. But we know that the KSP for this can never, ever, ever change. So we still need the 2.3 times 10 to the minus 13, but we just made the chromate gigantic compared to what it used to be. So it used to be 4.8 times 10 to the minus 7 chromates and 4.8 times 10 to the minus 7 leads. But now we have increased the chromate all the way up to 0.10. And so now to solve for this, we get the concentration of the lead equals that divided by that. Which brings us up to 2.3 times 10 to the minus 12 molarity. So again, I'm going to circle this, and I'm going to circle this. Okay. So without the common ion, the water will still hold this much lead. Okay? As soon as we put in the common ion, the amount of lead that the water can now hold goes way, way, way down, which makes more of it precipitate. So now we're going to have almost zero lead in the water, which will force it all to precipitate out, and then we can easily filter it to remove the lead from the water. And so basically you always have to run the math twice. You need to figure out what it is under normal conditions, and then you need to run the math again and say, okay, we have increased this ion because we added a substance with the common ion. We've increased one of them, so the other one must decrease. And you just got to be careful. If any of these have an exponent on them, you're going to have to keep track of that exponent, and you have to understand that if this had been CrO4 parentheses with a little 2, then whatever this number is would double going here. So for instance, if we did calcium chloride and we were going to do 0.10 molarity of that, when this splits, you always get 2 chlorides for every one of these you put in water. So back when we did net ionic equations, that was why this was so important. Because a 0.1 molarity solution of that actually gives you 0.20 molarity chloride ions, and that number would then go in here if chloride was your common ion. So you just got to make sure you don't violate any of the rules we've been learning as we've been going throughout the year. But as you can see, that number is bigger, this number is smaller, which is what the common ion effect says. If we increase one of them, it's going to force the other one to go the opposite direction. Okay? You can also do the same thing if you can find a way to get one of them to be removed. The other one will have to go up to compensate for it. So make sure you do as many of these as you can to get good at it. There is one of them on your quiz, so make sure you are ready to go before you start that.